Welcome back, students. In this video, we're going to talk about properties of compounds, and we're going to start with how intermolecular forces affect properties. Let's start with boiling point. When we look at boiling point, this is how much energy it takes to break the intermolecular attractions between molecules so that your molecules can move from a liquid phase to a gaseous phase. So what's the relationship between intermolecular forces and boiling point? Well, the relationship between intermolecular forces and boiling point is as the strength of the intermolecular force increases, the boiling point increases. Stronger intermolecular force means higher boiling point. Where I'm abbreviating intermolecular force as IMF and boiling point as BP. So let's talk about why. Why is there this relationship? So when we consider boiling, what happens is you have liquid, where the liquid molecules, or the molecules in the liquid phase, are pretty close to one another. They're close enough that in the bottom right-hand corner, where I'm highlighting right now, they're showing these attractions. So the molecules are quite attracted to each other. If you think about molecules as being like magnets, if you have magnets that are close to each other, they can feel the attraction. If your magnets are far apart, they don't feel the attraction any longer. So what your goal is for boiling something is to take molecules that are in the liquid state, that are close together, that thus feel a strong attraction, and separate them, put distance between them, so that now in the gaseous state, they're further apart. When they're further apart, they don't feel that attraction anymore. So what that means is you had to break the attraction. So how we break the attraction is turning up the temperature. The temperature of the solution needs to be high enough that the molecules move fast enough that they can break free of those attractions. So the stronger the attraction, the higher the boiling point. And what I have on the left is two examples for you. So in this first example on the very left-hand side, what I want you to see is that you have polar bonds going this direction. So if we go back to our mental flow chart that we made a couple of presentations ago, where we now have, we're looking at the oxygen, we're trying to decide if this molecule is polar or not. We have a central atom that does have polar bonds, and there's lone pairs on the central atom. So this is a polar molecule. Is there an OH, NH, or FH? No. So it's just experiencing dipole-dipole forces. So this is going to have dipole-dipole interactions. Whereas ethanol on the right-hand side is going to probably experience a stronger intermolecular force because, again, if we look at the oxygen, we have the OH bond and the OC bond are both polar, and the oxygen is pulling electrons toward itself. So we have polar bonds and we have lone pairs on the oxygen, which makes this a polar molecule. So how do we know what intermolecular force it experiences, or at least the strongest intermolecular force? Well, it is polar and it contains an OH bond, right? So here is the OH bond. That means that this is capable of hydrogen bonding. So another ethanol molecule, which is the name of this structure, could be attracted to this one with hydrogen bonding. So this is capable of hydrogen bonding. So now that we know one of these experiences dipole-dipole, the other one, the strongest force it experiences is hydrogen bonding, we know that the stronger the intermolecular force, the more energy it takes to break that attraction, resulting in a higher boiling point. That this one is going to have the higher boiling point. How much higher, you ask? Well, let's put some numbers to it. So ethanol has a boiling point of 78.5 degrees, and dimethyl ether has a boiling point of negative 24.9 degrees, and those are both in degrees Celsius. So look at how much of a difference there is between the boiling points for these two molecules. The one that can hydrogen bond, 78.5 degrees Celsius, just about 22 degrees less than water. Whereas dipole-dipole interactions for the structure on the left, this one is a gas at room temperature, right? It's just has a very weak intermolecular force in comparison. Let's talk about how boiling point can also relate to size. Remember in the last video, we discussed how London dispersion forces end up getting stronger the bigger a molecule is. As we look at the left-hand molecule that has 4 carbons and the right-handed molecule which has 6 carbons, the one that has 6 carbons has more opportunity for attractions. So it's going to experience greater London dispersion forces. As a result, because we already learned on the previous slide that intermolecular forces, that the stronger they are, the higher the boiling point, we can tie that in here too. Because the bigger the molecule, the stronger the intermolecular forces. Bigger molecule translates to stronger intermolecular force. And what did we say on the last slide? That the stronger the intermolecular force, the higher the boiling point. Why? Because it takes more energy to break the stronger attractions, right? And that more energy means a higher temperature because you're putting in energy into the system that can result in those molecules moving and having enough kinetic energy to break the attractions. The molecule on the left, this is called butane. You'll learn how to name molecules later. This has a boiling point of 0 degrees Celsius. Whereas hexane, which has 2 more carbons, has a boiling point of just under 70 degrees Celsius. That is incredible. What a huge difference for just 2 carbons. A quick fun fact before we move on, butane is lighter fluid. The butane in there is liquid because it is under pressure, but when it's just out in the world, it will be a gas. Now let's look at boiling point and shape. If we look at these two structures, I want you to take a moment and consider the structure on the left. It has 5 carbons. We call this pentane. And the structure on the right also has 5 carbons. It also still has the same number of hydrogens. These two molecules have the same chemical formula, but they're going to have very different boiling points. Why? Because the structure that is more branched, the one on the right, this carbon in the middle can't really do a whole lot. It can't be a magnet. Whereas when you have your carbons right in a row, there's more opportunities for attraction. And so what we'll find is that branched molecules, things like the one that's on the right, are going to have lower boiling points because they have less opportunities to interact with other molecules. So if we compare some boiling points here, pentane is going to have a boiling point of 36 degrees Celsius, whereas this other molecule is going to have a boiling point of 10 degrees Celsius. That is such a huge difference for going from something that is just straight in a line to something that is branched. Let's go ahead and summarize the relationship here. Molecules that are branched do not have the ability to be attracted to other molecules as easily. So they have weaker intermolecular forces. And because they have weaker intermolecular forces, that means that it's easier to break those attractions, which relates to a smaller numerical value for boiling point. I'm going to go with lower. Great, we've gone through boiling point. Let's switch ideas now. So those two molecules on the prior page, they had the same chemical formula, but they were completely different molecules, and they had very different properties with respect to boiling point. So this leads us into an idea called constitutional isomers. Constitutional isomers are compounds that have the same chemical formula, but they differ in how the atoms are connected. And like we saw, this leads to different properties. So here I have ethanol and dimethyl ethers boiling point and melting point. They both have the same molecular formula of C2H6O. But the fact that ethanol has the ability to hydrogen bond means that this is going to have a much stronger attraction between other ethanol molecules than dimethyl ether, which looks like this. And we've seen this pair already, but now we're just summarizing the changes in a table and saying, isn't it crazy that these two things have the same chemical formula? All that matters, all that's different, is how the atoms are connected. For ethanol, you have that OH, which is very, very polar. Whereas dimethyl ether, you have a CO, which is polar, but not nearly as polar as the OH. And this leads to staggering differences in the boiling point and melting point of these two compounds. Now let's move into our last two ideas. We're going to start here with solubility and polarity. Solubility, we talk about this idea that like dissolves like. I remember hearing like dissolves like as a student and just being completely blown away. And I kept asking, like what? What is the like? And I was so confused. And it took a really long time for me to recognize that the likes meant polar dissolves polar and nonpolar dissolves nonpolar. Like polarities dissolve each other. Let's go ahead and say polar dissolves polar. And then the contrary is true, that nonpolar dissolves nonpolar. When you're talking about two liquids, when they dissolve or not dissolve, the question is, are they miscible? So when liquids are mixed with each other and they dissolve, the word for that is miscible. So here it says oil is nonpolar, water is polar. Are they miscible? So do they mix to create a homogeneous mixture? Do they dissolve in each other? And you've seen this in real life before, right? No matter if you like to cook or if you like to clean or if you like cars, no matter what, you have seen oil and water. It doesn't have to be cooking oil. It could be gasoline, right? It could be Vaseline. It could be salad dressing. You have seen that they create layers. They are not miscible. Why? Because oil is nonpolar and water is polar. They do not mix. Okay, ethanol is polar. Water is polar. Are they miscible? Yes, these are miscible. Ethanol is what we would call like alcohol, in layman people world. Vodka is just ethanol and water. If you've ever gone to Meijer and looked at a vodka bottle, there's no layers in there, right? It is all one solution because ethanol and water are polar. And vodka is just a mixture of ethanol and water, and it just tells you using the proof system how much ethanol there is to water. Latex is a hydrocarbon. right? Hydrocarbons are all carbons and hydrogens. So something that only has carbons and hydrogens in it only has nonpolar bonds and thus is a nonpolar molecule. Vaseline is a byproduct of oil refining, which means that it is also nonpolar because, oil is nonpolar. So are they soluble? The answer is a big yes. And I have a story about this one where I had met someone who was teaching people about safe sexual practices. And this person did not know that, and that was their job. They did not know that latex condoms will be dissolved with Vaseline, and that's why you can't use Vaseline as a lubricant. And this just blew my mind because I'm a chemist, and to me it's obvious, but it's not obvious to everybody. So make sure that you know your solubility rules. Another one, dirt is nonpolar, water is polar. Are they soluble? No, they are not soluble. If you've ever gone to a dry cleaning place, right, when it says dry cleaning, it's cleaning without water. It's cleaning with a nonpolar solvent. And so dirt is nonpolar and the solvent that they use is nonpolar, and they call it dry cleaning because there's no water involved. So then the question becomes, why do we use water to wash our dirty clothing? And the answer is we have something else in there too, soap. Soaps and detergents are compounds that are really special because they have one end that is hydrophilic, which loves water, and another end that is hydrophobic, which hates water or is scared of water. So when you see a soap molecule, they're usually drawn something like this, where the hydrophilic end is this part, and the hydrophobic end is this part. The hydrophobic end is all carbon and hydrogen. That's why it's hydrophobic, is because it's nonpolar. The hydrophilic end usually has a negative charge, so it's usually some kind of ion. And the hydrophilic end that has a negative charge, it's polar. It's as polar as you can get. Ions are as polar as you can get. Because it's polar, it dissolves in water, which is also polar. The hydrophobic end is a long chain of carbon and hydrogen, and because of that, it's nonpolar. And because it's nonpolar, it ends up dissolving in the dirt. And this is the picture of what happens. And the picture could be better now that I'm looking at it, where this is meant to be the piece of dirt, and this is meant to be your hydrophilic end. Over here, these little squiggly lines, that's your hydrophobic end. And so what happens is the hydrophobic end kind of, attaches itself to the dirt because they're soluble in each other. And then it creates this sphere where there's the hydrophilic end all on the outside of the sphere. And because the hydrophilic end is all on the outside of the sphere, it can be carried away by the water. And that's why soaps and detergents work. For soaps and detergents, you might be actually pausing and thinking, aren't they the same thing? And they are not. So soaps are technically made from like animal fats or things like that. Technically, you could also make them from human fat. It's a saponification reaction. You can also make them from oil, but if you ever see a soap that says it's vegan, right, it's vegan because it wasn't made using animal fats. It was made using oils only. Detergents are something different, whereas detergents' hydrophilic end has a different structure than soap's hydrophilic end. And detergents tend to be a little bit harsher on the skin. And detergents are kind of newer in the world of chemistry, whereas soaps have been around for quite some time, because all people did was they took fats or oils and they added lye, which is the old word for sodium hydroxide, and it undergoes a reaction called the saponification reaction to make soap. So let's wrap up with our idea of guidelines for water solubility. Our polar compounds that have only 1 to 3 carbons in them are going to be soluble in water. Things like ethanol, where ethanol had 2 carbons and then a polar end, those are water soluble. Once you start getting to 4 or 5 carbons, water solubility gets a little bit more difficult. They end up being slightly soluble in water. And then once you have polar compounds with 6 or more carbon atoms, these are going to end up being generally insoluble in water. If I bring a diagram over here where, let's say this is a polar end and it's not super polar, and then I have a very big non-polar part. As we increase the non-polar part of my molecule, it gets harder and harder for that molecule to dissolve in water. Water is polar, you need a polar molecule in order to dissolve in water. And if your molecule is 90% non-polar, then it gets really difficult for it to dissolve in water. In this video, we looked at how boiling point can be affected by intermolecular forces, as well as the size and shape of molecules. Then we looked at polarity and solubility. You want to be able to look at 2 molecules and decide if they're going to be miscible or if they're going to dissolve in each other. Then we asked ourselves, then why does soap work? And so we talked about the method of soap and why soap does what it does and how it cleans clothes. And then we reminded ourselves that sometimes things are not soluble in water. If you have too much carbon and hydrogen, so too much of a nonpolar section, you end up decreasing water solubility quite a bit. Thanks so much for your attention. I'll see you in the next video. This is Katoni signing out.